All right. All right. Hello and welcome everyone to the Reproducibility Challenge webinar for the SC21 Student Cluster Competition and Virtual Student Cluster Competition. My name is Lamaya Weekly and I am the SC21 Reproducibility Challenge Chair. So before we go to the main part of the webinar, I have a few announcements on behalf of the SCC chairs. First is please check out the Google FAQ announcement doc. All teams should have access to it, and I've dropped a link in the chat. The committee chairs, the competition chairs, and the application experts will post announcements there, and will also post frequently asked questions that they will be getting there. So it's pretty useful, and I encourage you guys to take a look at it every so often to see what announcements and questions get posted there. Also, if you haven't already accepted the invite to the VSCC SCC Slack channel in this SC21 Students at SC Workspace, please do so. And if you haven't gotten an invitation, please send an email to the email that you see in the slide deck, student-cluster.competition@info.supercomputing.org. I've also dropped that email address in the chat. I encourage you guys to use these resources to take a look at the announcements and whatever information that the application experts are giving you and the committee members are giving you. I myself will be using these resources to make announcements about the Reproducibility Challenge. In a couple of weeks, I'll most probably be posting instructions for the report and a test data set, as well as some other resources that you guys might find useful, such as past reports from past challenges. So please take a look, make sure you have access to it, and yes, just please use these avenues for communication with the committee. So on today's agenda, I'll go through some introductions. I'll introduce who our speakers are outside of myself, and I'll give a brief introduction on what the Reproducibility Challenge is and what you can expect. Then we'll go through the speakers in a certain order, and then I'll finish up with some Reproducibility Challenge recommendations and some things to look forward to. And time permitting, of course, we'll do Q&A, and I'll try to monitor what's going on and see if we have any questions that come up in between some speakers. So outside of myself, who do we have speaking today? We'll have Michaela Taufer, who is the founder of the reproducibility effort at SC, and she'll be talking about the impact and importance of reproducibility in the field of HPC, scientific computing, and scientific discovery in general. Following Michaela, we'll have Stephen Harrell, the SC21 Reproducibility Journal Issue Chair. He'll talk a little bit about that when he speaks about the reproducibility life cycle of a paper, an accepted paper at SC. Stephen is also was the Reproducibility Challenge Chair from last year, so he comes with a great deal of knowledge about this part of the competition. Carlos Maltzan follows Stephen and in their speaker list, and he is this SC21 Reproducibility Chair. He'll talk about the current efforts that his committee is pursuing in the conference for this year, and his committee has taken quite a few strides in promoting the advancement and the impact of the initiative within SC and other HPC conferences as well. So he'll talk a little bit about that. Following Carlos, we have the author of the Reproducibility Challenge paper, Ankit Srivastava, the person who created the application app, the reproducibility app that you guys will be running. He'll be talking about the motivation behind the paper, the algorithm involved, the real life applications of the paper, as well as, and maybe that's most important for the teams to hear, the experiments and the results that he presents in the paper. So what is the reproducibility challenge? So the reproducibility challenge, or the reproducibility application, is one of the applications that you'll be running as part of the student cluster competition, or the virtual student cluster competition. In addition to other applications such as cardioid and quantum espresso, which I think that some of you may have attended the webinars for those that have taken place earlier. And if you haven't, you can take a look at the recordings that are on the SC21 website. And also you'll run the mystery application, which will be announced at the competition, and of course the various benchmarks that you'll be running on your clusters. For the reproducibility challenge in particular, you'll be attempting to reproduce part of the results of an accepted paper from the prior SC. So Ankit's paper was accepted in SC20, so you'll be attempting to replicate or reproduce part of the results in the paper that was accepted in the prior SC. What sets the reproducibility application apart from the other applications and the benchmarks that you'll be running in the competition is that instead of your scores being based on the results that you find, the scores from the challenge are based on the written reports that you will submit, along with a digital artifact that contains the scripts that you run in order to do the challenge, and descriptions of how to run these scripts or how you ran them in the competition. So we're not looking for the strength of the results that you find when you're running these the application and how much you can replicate the results, but the strength of the paper that you are writing. For many of you, this might be your first encounter with, for many of the students in the teams, it might be your first encounter with a technical paper, and it also might be your first encounter with writing or attempting to write a technical paper. So these are things to keep in mind when it comes to the reproducibility challenge versus the other applications that you might be running, that you will be running in the competition. Another thing that's interesting about the reproducibility challenge that Stephen's going to talk about a little bit more, I believe, is that the highest score reports will be invited to come back next year with and be shepherded to create, to bring their reports up to technical journal quality. And we'll invite Ankit to, along with your results, extend his paper and comment on the results that you found and how maybe this has affected his results, etc. So it's another publication, and it kind of completes the story of reproducibility of Ankit's work. So that's just what is a basic introduction to what the reproducibility challenge is. Of course, if you have questions, please drop them there. But now, and at the end, I'll talk more about what this report entails and give a brief description of that. But now let's move on to the speakers. So our first speaker, as I mentioned, is Michaela. So
thank you, Lee-May. And we can go to the next slide. Thank you so much, Lee-May, to inviting me here. And I want to thank all the participants. You all have such an important role for the scientific community and for the HPC community. We are learning from what you are doing through this reproducibility initiative. And you are also a role model for others. You are showing us what does it mean reproducing results and learning from that result. So thank you so much for that. Now, I am invited to this webinar every year, and every year I think is one of the parts that I like the most is the first step towards your effort, your work. And one of the questions that I had in the past was, why do we care about this effort? Why do we care about reproducibility? And so I want to go a little bit out of our domain, from the domain of the high performance computing community, and go in a community, in other scientific community, like in chemistry, in biology, and many other domains that are providing us with services like drugs to fight diseases, new materials, and many other things that are beneficial for our society. And when we look at how their results are executed and presented, they end up in journal, first of all, like Nature, Science. And one thing that is a valuable question for this result is, do we trust them? Do we trust the result, the experimental results that our colleague in chemistry, biology, and many other fantastic sciences propose to us? And so we do, because we know that behind that result, the experiment that is presented was replicated many, many times. And in that replication and reproduction, there is a convergence of conclusions. Can we go to the next slides, please? The other thing that is important that we keep in mind is that we trust also these results because they are well documented. And so normally when we look at these results, the paper is a part of the documentation, but there are other aspects that are like notebooks where the scientists in the wet lab put down all the steps one at a time and document them. So indeed, the aspect of documentation is very important. Next. So what do we get out of these experiments in these domains? Well, we get out that we can reproduce this experiment. And in reproducing, we can replicate the generation of the products that are coming out of this experiment. But another important aspect that we sometimes forget is that we also enable other colleagues to do the same experiments. And not only scientists in major corporation or a major lab, but also students at the university. And so this is an important aspect of us growing professionally through the replication of work of others. Can we go to the next one, please? So now we have spoken about fields that are not our domain. We have spoken about biology, chemistry, and many other sciences. And we spoke about experimental results. Now let's make a small exercise and replace experimental results with computational results. Results that are targeting scientific problem, but are generated by computer, by supercomputer, like it is in high performance computing. And so the question repeats itself: do we trust our computational results? And what is the benefit of being able to replicate and reproduce our results? These are important questions that are important question to answer, because high performance computing and the resources behind high performance computing enable so much in the scientific domain and in our everyday lives. So why do we care about this effort? Because we are at the front end of a new way to look at how computational science and high performance computing can contribute to the everyday lives of everybody. So thank you so much. I hope I convinced you a little bit more. I'm sure you are already on board, but if you were not completely, I hope I convinced you that what we are doing is so important and what you are doing is so important. So thank you.
Yeah, I thought I was unmuted. Thank you so much, Michaela. That was great, and I hope the students are feeling the importance of this and can carry this through for the challenge. So next up, we'll have Stephen Harrell to talk about the history. Stephen.
Hi. So I'm really just going to talk about the life cycle of reproducibility at SC. And so this slide sequence is going to kind of go from left to right, and it's going to go down and right to left. So just FYI, it's a little bit weird. It's a circle with no curves, I guess. This year, we actually added another badge. Carlos and his team worked very hard to do that. And so now we actually have 3 badges that we're giving out. But this is basically how we start the process. So the technical program gets papers submitted, those get accepted, and then we look for candidates within those, especially ones that are badged. to be candidates for this challenge. Next slide, please. So we select one paper for the SCC for the next year. Next, please. Thanks. So we take that paper, and this year it's been Lee Mai that's been doing this, and she's generating a benchmark based on the paper and based on what is possible to reproduce. Of course, not everything in HPC is reproducible because of a lot of reasons, but we want to make sure that even when we face those kind of strong issues, that we're still doing what we can and finding new ways to make things reproducible. And I think that's a key component of what Lee Mai is doing. Okay, so then you go to the student cluster competition. That'll be in November. And I think you guys know a lot about that already, so I don't think I need to talk too much. So let's go next. And then we assign a very special badge, which is the results replicated badge. Carlos, you can correct me if I'm wrong, but so far, or Michaela, so far I only know that we have given away this badge. Is this badge even given away by other people for other things? I think we're kind of unique in that way. Certainly it's available for other conferences to use if they actually did the work. Is that right, Carlos? I see. You're muted, Carlos.
Sorry, that's the same problem. I don't think we're unique in that we are the only ones who give that badge. There are other efforts where you have publications that replicate the results of others, and then the paper that has been replicated gets that replicated badge. So that does happen already, but it's, you know, I would go a little bit more in detail, but this is really a fantastic effort that Michaela started here.
Okay, great. We'll look forward to that in a minute. So once we and then we give a certificate to the author. So Ankit will get a certificate this year at SC21, and then we do the journal. So I'll take this minute to talk about the journal. Lee Mai went over it briefly, but the basic overview is that you'll write reports as a part of this competition. Your reports will be graded as a part of the competition, and then whoever is the reproducibility chair for the reproducibility challenge chair next year will take those reports and the grades and decide where a natural cutoff is, and then invite the teams with the highest scores to participate in this journal. And what that means is you'll take a technical report and you'll turn it into a journal quality article, and that can include a lot of things. And as Lee Mai said, this is probably the first paper for many of you, and we really like that. Yeah. And then we'll have Ankit hopefully write in an additional 30% talking about the outcomes from additional 30% of his original paper to talk about outcomes from what the teams did, interesting things that happened, and also reflect back on his experience with going through the entire process of writing a paper that is reproducible and then actually helping people to reproduce it. And I think that's really great. So that's the basic overview from the journal right now. I'm happy to take journal questions after I'm done, if you like. Can we go to the next? And then we publish that basically in IEEE TPDS this year. We don't have a commitment from them next year yet. We hope to, but each year it's a provisional thing. So as long as I do well, then I think it won't be a problem. So yeah, I think that's the entire life cycle, and then we kind of start back over at the technical program again and just go through the whole thing. So Michaela or Carlos, did I miss anything? Does that seem like a good summary?
I think so, Stephen. I want just to point out how exciting it is for you all to have a publication when you are an undergraduate student. Some of you may have others. Some may be exposed for the first time to have a publication. And if you want to go for a master or a PhD graduate school, having a publication in your CV makes such a big difference for many schools. So that is something that helps you for your future as well.
That's a good point.
Yes.
Are there any? Oh, go ahead, Levi.
No, that was nicely put, Michaela. Yes, go ahead, Steve.
So, I guess I was just going to wrap it up. So, if there's any questions, I can take them now, or happy to move on. Okay. Well, thank you.
Thank you, Stephen. And now we'll move on to Carlos, who will talk about, again, the Reproducibility Initiative in SC21.
Thank you, Lemai. And I want to thank you and also Steve and also Michaela and Steve Leek for your great work in keeping this pipeline from reproducible papers to actually replicating that work in the student cluster competition. When I was asked to be the chair for SC21 Reproducibility Initiative, I felt very honored to step sort of in the footsteps of the past 5 years of people who've been driving the reproducibility in supercomputing. And I want to talk a little bit about the history of that. So next slide. The Reducibility Initiative got approved by the steering committee in 2015, but it was actually too late for the submissions to actually include any kind of reproducibility information. So it was thought the papers were asked to do this after the fact. So they were already published and the conference presented, but then they were able to actually add some additional information about their artifacts. And that was called the artifact description, or AD appendix. But right away, as Michaela, who was chairing this, she introduced the student this trick of having actually the student cluster competition to try to replicate some of that work. And that is very unique. That is something that no other conference has established. This connection directly from papers that were presented at the conference to students trying to replicate that work. So that's it's a really nice innovation. And in SC16, the application. The artifact description appendix was still optional. It was for the first time, authors were able to submit information at submission time. And in 2017, the artifact description was still optional, but only papers that had that artifact description could be considered for best paper or best student paper awards. So you see sort of a tightening of more, encouraging more people to have these artifact descriptions as part of the papers. And then also in SC17, the first time was introduced this computational results and analysis appendix, which was then renamed to the artifact evaluation appendix in SC18, and that name's stuck until up to now. And the artifact descriptions were also extended to workshops and posters. In 2019, we saw that for the first time, the artifact descriptions were mandatory for all submissions, and that also meant, and based on the experience of previous years, the submission was standardized with a form. Furthermore, the committee, the Reproducibility Initiative, started to get more structure, right? And so 3 new subcommittees were introduced. Which are the 3 subcommittees that you see today? One is for artifact description, artifact evaluation review. One is for the student cluster competition, the reproducibility challenge in the student cluster competition, and one subcommittee for the journal special issue. In SC20, you see even more, again, progress where the reproducibility initiative was extended to also or focus on transparency, especially for research involving AI, and further streamlining of the artifact description appendix, and then also there was a formal survey among the community to see what people think about SC reproducibility. And one of the major results was that transparency was very important, possibly more important than reproducibility by itself. And I think that that's very important, right? It's a very important goal of reproducibility to actually create greater transparency, just like Michaela also said at the beginning of our session. So in SC21, we, next slide, please. Ivo, the vice chair of Reproducibility Initiative, and I quickly decided to focus on artifact evaluation. That was sort of been a little bit of stepchild of the Reproducibility Initiative in the past years, and we wanted to really see, can we push this forward? And the way we tried this is by involving other, pulling in people from other conferences. And people who were very much experts in artifact evaluation, and see whether they can maybe move this forward by adopting practices from other conferences. And so Tanu Malik from DePaul University, and Anju Waldik-Oberwagner from research labs in Intel did a fantastic job in doing just that. Anju in particular has experience at OSDI, at SASB, and also at security, and that continues also in other conferences. So he comes in from other systems conferences that are not necessarily HPC related. So he's actually has no background in HPC. His specialty is actually security, but he brought in a set of practices that I think are very valuable. One of the things that they achieved is a clear separation of responsibilities between the ADAE review committees and the technical program committees. The technical program committee are the ones that, as Stephen already showed right at the beginning, they review the papers, right? They are the ones that decide what paper to accept and what paper to reject. And so there's a potential conflict between the people who look at the artifact description and artifact evaluation appendices of these papers and think if something is really unacceptable, and yet the program committee is saying, oh, this is a great paper, we should accept it, right? So there's like, who has authority? And the way we resolve that is to split the 2 steps and 2 phases. And you can see this in this little diagram. Basically, there's artifact description evaluation, which is mandatory. And we basically, the ADAE review committee is just providing a signal to the TPC whether something is acceptable. This is a very interactive process, by the way. So at the beginning, when papers were submitted, about 50% of all submissions were actually had unacceptable artifact description. And that would have been, you know, if you would have just stopped right there, you would have rejected 50% of all submissions, which is of course not a good thing. So we wanted to, but it was actually very easy to fix. So within 1 week, it was down to, I think, 10 papers that still needed work on their artifact description, and which was a huge reduction in percentage. I think it was like over 300 submissions. And then and then at the end, I think we ended up with like 7 papers that didn't have a good artifact description. The second part was that in order to get a badge, you had to actually apply for it. So only papers that were actually accepted in the first phase, right, by the technical program committees, and but had a badge application of any of those 3 combinations of those 3 badges, were considered by the ADAE review committee. And it turns out 50% of the submissions actually also applied for these badges. And that again was also a very interactive process. It takes about, for a reviewer, a week to evaluate these artifacts of these papers. But the end result is that there's a lot of papers that have really good artifacts. And so,
sorry to interrupt you. We're a bit halfway through time. So I just wanted to make sure we have enough time for Ankit to get through his presentation.
Yeah. All right. I will wrap up really quickly.
Sorry.
I want to basically say we introduce also infrastructure for artifact evaluation. And next slide, please. So we have 3 badges. Next slide. And I want to quickly talk about the Reducibility Advancement Award that was approved just a couple of weeks ago. I'm really happy about that. One of the things that was a big influence in the approval process was that a lot of other conferences had actually these reproducibility awards as well. But it's a big deal for supercomputing to have an award for reproducibility, because it actually enshrines the value of reproducibility in the conference. It basically provides the motivation for the next conference years to select these papers, the best papers that advance, or the best artifact that advanced reproducibility the most. And next slide. We have a selection process that involves both the technical program chairs, as well as the committees and the ADE review committees, as well as the reproducibility challenge and special issue journal chairs. We did this because the papers that are either self-nominated by authors or that are nominated by the various committees provide another very strong signal of what papers to select for the next reproducibility challenge, right? And it's sort of one of our contributions to streamline that process and make it easier for future chairs, likely my, to select those papers. Anyways, that's it. Sorry I took so long. Thank you so much.
That was great, Carlos. And I think it further highlights how reproducibility is important and is moving forward and gaining more traction, and people see it as important. And you as students will most probably encounter, if you decide to keep going in this field or in the field of science, will keep encountering these ideas and these reproducibility initiatives. So I'm going to stop sharing, and we will have our application author, Ankit Srivastava, give his presentation. So Ankit, please take it away.
Is my screen visible? Yeah. Okay. Thank you, everyone, and hello. I'm Ankit Srivastava, and I'm one of the authors of this SC20 paper named A Parallel Framework for Constraint-Based Bayesian Network Learning by Markov Blanket Discovery that led to the development of this application, Ramble, that you'll be working with for this year's Reproducibility Challenge. So what motivated us to do this work? So as we are all probably aware, we are constantly interacting with machine learning models because they are being used for decision-making in a diverse set of fields. And when I sat down and thought about how I interact with machine learning models, the two most common examples that I came up with were spam detection that's implemented using machine learning in email clients like Gmail and Outlook, and also it's used to implement recommender systems for recommending movies and TV shows by Netflix and Amazon Prime or other streaming services. Now, most of these models that are being used in production these days are known as what referred to as Blackbox model. And the reason for that is it's kind of, this comic kind of pokes fun at the idea of how they learn. But the idea behind, the basic idea behind learning these black box models is that they learn some representation using a data set and then use that learned representation to perform a related task. And a common example of that is deep neural networks. And this is how deep neural networks work, which is to say that these models are not very interpretable. So if we want to understand why the model predicted something for a particular data point, given the current state of research, it's not possible to do so. And this does not take away from the efficacy of these models, which, so these models are very popular and are used in a variety of fields, as I said on the last slide, and they outperform almost all the other models for a variety of tasks. So they're very good at what they do. And it's not a problem if they make a mistake while recommending movies or TV shows, because it's a minor inconvenience. It's not really a life-changing event. However, it does become a problem when these models are used in high human impact areas, such as for deciding whether a person stays in jail or deciding whether someone should be provided healthcare or deciding whether someone should be arrested. So in these cases, when these models make a mistake, it makes it a news headline, and rightfully so, because it affects someone's life. So it's fair to say that apprehensions regarding the use of such black box models, at least in these high human impact areas, is growing. So interpretable machine learning models are the need of the hour, and now more so than ever, because just in the last 2 or 3 months, multiple regulatory agencies such as European Union, US Federal Reserve, Federal Trade Commission have come out with guidelines regarding the use of such black box models in production environments, because they don't provide the explainability that might be needed in a lot of areas. So interpretable machine learning models are needed, and one such model is Bayesian networks that allow interpretable decisions because they enable probabilistic reasoning about links between the variables of interest. And they have already been successfully used for applications such as for diagnosing illnesses, for reasoning in legal scenarios, epidemiology, and other high human impact areas. So what is the problem then? The problem is that learning the structure of Bayesian networks is computationally intensive, which is where we think parallelism can help. So while there do exist libraries for learning Bayesian networks, they don't support a lot of parallelism and correspondingly take a long time to learn even moderate scale Bayesian networks, as we'll see in the results section. There have been parallelization strategies that have been proposed for various learning algorithms, but they are difficult to integrate into a single library. So when we set out to do this work, we wanted to have a single parallel library with support for multiple algorithms that can be used by domain scientists or ML researchers to learn large-scale Bayesian networks. So what are Bayesian networks? So for the purpose of this presentation, Bayesian network can be thought of as a dependence graph over a set of variables. And so let's look at a case study where, because Bayesian networks have been used to model stock prices in the past, I wanted to show this stock example where I talk about the stock prices of cloud-related companies. So for example, let's say, this is just a thought example, I'm not claiming any knowledge about these companies here, but it's kind of intuitive to think about it. If NVIDIA, for example, supplies GPU to all the cloud companies such as Google, Microsoft, and Amazon. So if NVIDIA prices go up, all these prices go up, or they're somehow related to it. So it's intuitive to think that these prices are somehow related. So there is a directed relationship between these 4 companies. Then we know that Netflix uses Google and Amazon cloud services for its cloud service, for its streaming services. So maybe Google and Amazon affect the stock prices of Netflix. And similarly, Spotify, because Spotify only uses Google, Spotify's stock prices might be different by Google. So over these 6 variables, this is a Bayesian network, which is a directed acyclic graph, or DAG, where we have a directed arrow between 2 variables. So some terminology now: parents and children set of a variable consists of the variables that are dependent on it given any conditioning set. And in the DAG, it corresponds to the parent of a variable. So for example, for Google, highlighted in blue, NVIDIA is its parent, so it's in parent and child set, and Spotify and Netflix are its children, so they are also in its PC set. Then another thing that we look at is the Markov blanket of a variable, which consists of the variables that render the variable independent of all the other variables in the network. And under some assumptions, the Markov blanket of a variable consists of the PC set of that variable, as well as the parents of all the children of that variable. So in case of Google, because Amazon is a parent of Netflix, which is its child, so Amazon is also part of the Markov blanket of Google. So with that background, we come to the focus of this paper, which was on parallelizing some blanket learning algorithms. And blanket learning algorithms, there's a huge hierarchy of all the different Bayesian network learning algorithms, and I would not go into all of them. But blanket learning algorithms are the type of algorithms that learn Bayesian networks by conducting repeated tests of conditional independence between the given variables. So they learn that dependence variable between pairs of variables. So, and that is done using by conducting statistical tests using a given data set of some observations for the given variables. And we denote the number of variables by n and the number of observations by m. And in this paper, specifically, we looked at discrete data sets. So we use G-square test, which is very commonly used for this purpose in constraint-based space. And blanket learning algorithms are a type of constraint-based algorithms that first learn the Markov blankets of all the variables separately, and then combine them to get the Bayesian network structure. And I'll talk about how they do that sequentially on the next slide. But the 3 algorithms that we focused on in this space were grow-shrink algorithm, or GS, incremental association Markov blanket algorithm, or IAM, and interleaved IAM, or inter-IAM. So these 3 are the very popular algorithms in this space, so we focused on parallelizing these. So let's see how these algorithms work sequentially. So they've used a variation of what is known as the grow-shrink scheme for learning Markov blankets first. And this is done separately for all the variables. So in the grow phase, variables are added to the candidate MB set, and in shrink phase, false positives are removed. So in grow phase, might add some false positives, which are then removed in shrink phase. And these 3 algorithms differ in how the scheme is iterated. So we, IAM and inter-IAM, choose one heuristic, GS chooses another heuristic. They also differ in how these grow and shrink phases are executed. So for example, GS and IAM execute multiple grow phases and then one shrink phase at the end, whereas inter-IAM interleaves the 2 in order to prevent too many false positives from getting into the candidate set. Then you might have noticed from the toy example that Markov blanket is a symmetric relationship. So symmetry correction is performed. And then because PC parents and children set are a subset of the Markov blanket, we can kind of prune out the variables that are not part of the PC from the MB set to get the PC. And once you have the PC, it's like the direct, my direct descendant for all the variables, and you can combine them to get the complete Bayesian network structure. So for parallelizing these, there have been a few related works that I've looked at, parallelizing constraint-based algorithms. So Nikolova and others in 2011 parallelized two similar constraint-based algorithms, and their solution scales well up to 512 cores for learning neighborhoods of 1,000 variables, which is less than what we wanted to do. We also saw that their solution, the scaling of their solution tapers off as the number of cores or variables are increased, and we'll see why that is the case. BLlearn, which is a popular software for learning Bayesian networks sequentially, and somewhat, so they implemented in 2017 a parallelization scheme which uses a master worker paradigm for very small scale parallelism. So their solution also does not scale well. And both these approaches distribute learning of variable neighborhoods. So let's see how that works. So again, a toy example for learning the Markov blankets of 6 variables, let's say, which are distributed on 2 processors. So on each processor, we have, if the total number of variables is n, then we have n by p variables on every processor. And typically, we'll have all the other variables. For every variable, we'll have all the other variables as candidate for the addition to its Markov blanket. So we have 5 candidates for all these 6 variables. So work per processor is then n squared by p on every processor. So let's see how this works. So let's say in iteration 1, I have these candidates. I use some heuristic to pick a candidate for the Markov blanket for every variable, add it to the Markov blanket shown in green here, and remove that from the candidate set, and then go to iteration 2, pick some variables, add it to the candidate Markov blanket for the variables, for the corresponding variable. But now we can see that the last variable did not pick anything, and that's possible in a real example or while learning a real Bayesian network, which means that no other variable can be added to its Markov blanket. So in the next iteration, we remove all the candidates for that particular variable. But now this creates a problem with this approach because there's a load imbalance, because the first processor will now do computations for 3 variables, whereas the second processor will do the computations for 2 variables. This does not seem as bad, but as you can imagine, in a real world scenario, this can be way worse. And it's unclear how to fix it because we cannot move a variable from the first processor to the second processor, because then the problem will remain just as bad. So let's keep moving though. In iteration 3, we again pick one for the first variable. We pick a candidate to add to the Markov blanket. Now we just have one variable left that still needs to learn its candidate Markov blanket. So now we'll have an idle processor, and this is because of the coarse-grained work distribution with this approach. So the observation from this that we made was that variables have different neighborhood sizes. So distributing variables to processors is suboptimal. And so we use this key idea, which is very simple, which is to distribute all the target and candidate variable pairs in parallel instead of just learning neighborhoods for different variables. So let's see how that works. So again, we have a similar setting. I have arranged these pairs similar to the previous example. And now we can see how the work per processor remains the same. And now iteratively, in the first iteration, we pick the candidate pairs, move to the second iteration, again, pick some candidate pairs. But now the load imbalance that appears again, that can be alleviated by moving pairs across processors, because we have all the information to learn them independently. And we can also avoid idle processors by moving pairs around. So we implement this idea using a primary data structure that we use, which is a list of tuples where we have a target variable, a candidate variable, and the corresponding score for that addition to the Markov blanket. And we distribute it, block distribute it across processors in parallel in order to do this in a distributed fashion. So using this idea, I would not go over in detail about all the design of these phases, but we proposed parallel implementation or parallel algorithms for all these different phases, combining which we could implement all three algorithms. So we propose a parallel algorithm for GS and IAM, and a different one for inter-IAM, and that's because the inter-IAM interleaves the grow and shrink phases in every iteration. So with that algorithm, we implemented it. Obviously, wanted to have a good implementation as well. Just having a good parallel algorithm doesn't suffice. So we implemented it using C++ and MPI, and the implementation is available on GitHub. And we also implemented a bunch of optimizations for fast execution in practice, which included some algorithm-specific optimizations for GS, which we'll see the effect of in a minute. And we also experimented with different statistic computation strategies for conducting these conditional independence tests, because that's like one of the most computationally expensive part of this whole process. And we also implemented a dynamic load balancing scheme, which used the fact that we could move the C scores or the tuples in the C scores around to fix the load imbalance. So for our experiments, we used 64 nodes of the Hive cluster at Georgia Tech, and on each node we use a maximum of 16 cores and assign 16 MPI processors, pin those processors to different cores, and so use a maximum of 1024 processes for our experiments. In order to show the efficacy of our implementation, we used this construction of gene regulatory networks from gene expression dataset, which is a very common use of Bayesian networks even today. So in this problem, genes are modeled as variables, and we in wet labs, biologists observe the expression values for these genes, and then based on those observation values, we can learn gene regulatory networks for different organisms, and there are different usage for learning gene regulatory networks for different organisms. So in this particular case, we use 3 different data sets of different sizes for yeast and Arabidopsis thaliana, and they were of, as you can see, there's a good variety of different number of variables and observations. Further, we used 3 simulated data sets, which were a little bit bigger than the biggest real data set that we had. And all the 3 simulated data sets that we used had 10,000 observations for 30,000 variables each. So first, we compared sequentially our implementation with the prior state of the art, which was BLlearn. As I mentioned earlier, it's a popular library for learning Bayesian networks. And even though it's an R library, it has a C backend implementation. So most of the algorithms implemented in BLlearn are pretty fast. So when we compared our runtimes with that of BLlearn, we saw that for IAM and inter-IAM, we got up to 2.8x sequential speedup for IAM and inter-IAM. For GS, we saw that BLlearn could not learn the network for the 2 bigger data sets within 4 days, which is shown by an X for D2 and D3. And so our implementation was much faster than BLlearn for GS specifically. Another thing to note here is that just looking at the sequential runtime of our implementation is that the optimization that we implemented for GS allowed our implementation of GS to be faster than our implementation of IAM and inter-IAM. So you can see for D1, all 3 data sets, it's almost 3x, 2 to 3x faster. So IAM and inter-IAM runtimes are similar, whereas GS is 2 to 3 times faster than the other 2 algorithms. We also wanted to have our software output the similar networks as BLlearn, and we ensured that that was the case as well. And then we also evaluated the parallelism of BLlearn, but found that even using 64 cores, BLlearn only provides 4x speedup, and this is self speedup, which is so we measured this speedup as compared to the BLlearn sequential runtime, which is already slower than ours. So we did not evaluate its parallel scalability any further, and we went to evaluate the parallel performance of our framework. So in order to evaluate the parallel performance, there are generally notions of scalability are used, and the two most popular ones are strong scaling, where you want to see, given a fixed total work, how, when you increase the parallelism, how does the runtime scale? So we are given a fixed problem size that possibly takes too long to be really feasible in a real world scenario. So we want to increase the parallelism and possibly reduce the runtime. And we want to see how that, so that is known as strong scaling, where n is kept constant and p is increased. The other notion of scalability is weak scaling, where we keep the work per processor fixed, and then we want to see how does the runtime scale with increasing parallelism. And the idea here is to try and solve bigger problems than were possible sequentially. So in this case, n is increased as p increases. So both are increased, but in order to keep the work per processor fixed. And in both these cases, a good parallel implementation would show linear speedup and 100% efficiency. And as close to that as possible would be, that's how good a parallel algorithm or the corresponding parallel implementation is. So first, we looked at the strong scaling of our framework for IAM. So on the left, we see the strong scaling speedup plot. And on the right, we see the strong scaling efficiency plot. So we see that, so these are kind of, you can generate these plots from the same data points. So let's look at the efficiency. So efficiency is for D2 and D3, the two bigger data sets, it's above 80% using IAM. For D1, it falls, it starts falling close to using, when we are using more than 256 cores. And that's because for D1, you can learn the network within 4 seconds using 256 cores or more. So communication overhead takes over at that point. We saw similar scaling pattern for inter-IAM as well. For GS, however, we saw that even for the bigger data sets, the scaling is pretty bad. So the scaling goes to 40% on 1024 cores as compared to the other two algorithms. It's pretty bad. I shouldn't say it's objectively bad, but it's as compared to the other two, it's not great. So we investigated this further, and in order to do that, we measured the runtime that these implementations spent communicating as a fraction of total runtime. So we see that this plot is for D2, and we see that GS spent more than 80% of the run, or close to 80% of the runtime on 1024 cores communicating, which we kind of expected because we had optimized GS to reduce its total work. So we kind of expected it because possibly there's not enough work for GS to do on higher number of cores. So this was our hypothesis, and we tested it out using simulated data sets, which were bigger data sets, so potentially required more work to learn. So the left plot shows a strong scaling efficiency for real data sets. For simulated data sets, however, GS also showed good scaling efficiency of above 60% for all 3 simulated data sets. So that was good. Now, next, we evaluated the weak scaling of our framework. And in order to perform these weak scaling experiments, we need to keep the work per processor fixed. So how do we vary n when the p is increased? So the approach that we took was, because we had a limited size data set, we chose all the variables when using the largest number of processors. So on 1024, for example, if we use D2, we would use all 18,300 something variables, and then use a subset of variables when executing these experiments for smaller number of processors. And as we discussed in the toy example, the estimated work per processor is n squared by p. So the chosen number of variables was scaled as root p. So you can use this formula for, we use this formula for choosing the number of variables on smaller number of processors. And in all these cases, in all our experiments, we chose the first NP variable. So if it's 100 variables, then we always choose the first 100 variables, because the variables that are chosen shouldn't really matter for these experiments. So it doesn't really matter which variables we choose, but so we chose just the first X variables. So weak scaling plots, these are weak scaling plots for D2, which show kind of similar pattern to strong scaling, which seems to suggest that communication overhead is again a limiting factor for weak scaling. So on higher number of processors, because the communication requires more time, the scalability would decrease. So with that, I would kind of summarize results. So we developed a parallel algorithm and implemented it in a manner that genome scale Bayesian networks could be learned in less than a minute using 1024 cores, which was down from more than 13 hours sequentially using our optimized sequential implementation, whereas using prior state of the art, it could have taken more than 4 days, as we saw for BLlearn. And it showed good scaling efficiency for both IAM and inter-IAM. And for GS, we saw using simulated data set that took less than 2 minutes to learn on 1024 cores as compared to more than a day sequentially. So with that, I'll thank you for your time and take any questions.
Thank you, Ankit. We're pushing up against the time. We're actually a little bit over time. So I just wanted to quickly go over my slides, last few slides. And I think they might cover a few of the questions as well that are in the Q&A, the document that Steve posted. So let me quickly go over my slides, and then I hope that they addressed also a few of the questions that, that were asked. So as I mentioned, you guys will be submitting reports. So what should you expect in these reports? And when I share some of the examples of previous year's reports from the special issues, you might get an idea of what it is. But you will expect to describe your architecture, your hardware and your software stack that you're using, the experimental setup, the experimental design, so the number of runs, the implementation, how you chose the runs, how you did those. You should expect to plot and describe the outcomes of your runs and your experiments and compare them to what you see in the paper, and also frame them in the idea behind this challenge of reproducibility. So what are the differences between what Ankit did in the paper versus what you are seeing, etc. So preparing for the challenge ahead of time. And again, as I mentioned before, this might be your first encounter with a technical paper and writing a journal quality paper as well. So start early. The September 17th deadline to give your infrastructure is going to be coming up. So these things are getting firmed up. So write what you can. You can talk about what your infrastructure is like, what the architecture is, and what you're planning to use for your software. Again, I'll be sharing some old reports, so take a look at that. They will be the chosen highest reports from that year. So take a look at what the markers they have that made them special, and maybe the intersection between these reports that qualified them to be so high ranking. Right. So again, take a look at the Google FAQ announcements page and the Slack channel as well for these announcements. Ankit went into what experiments he did and what results he presented. And also his GitHub repository is available, so you can take a look at what the code looks like now. So try out some weak and strong scaling with those applications ahead of time. Try it, and when you're doing this, think about the design of the experiment that you want to do. You'll have an idea of how it runs with certain data sets. I will give a test data set out in a couple of weeks. So try that out. Think about the number of runs, the minimum number of runs you'll have to do in the competition to get the results or to reproduce the charts that you'll need to reproduce. And write up what you can about what you did or what you plan to do ahead of time, right? Think about the structure of report and what you want to place where. And most of all, ask so there was a question in the the Google Doc that Steve posted about what is the faculty members or the team sponsors contribution to the writing the report. Well, it would be advisory, right? Invite the student team members to be curious and ask, and while they're running these weak and strong scaling experiments with the test data set that I will give you, have them think about why do you see these differences? What could be the reasons for these differences? Again, the reports, we're not going to score them on how close your results look like to Ankit's, but what are the differences? What did you notice? What were some of the showstoppers? What could account for the differences? Did you see the same results? If not, why? There's a lot of things you can look at. The architecture that you're bringing, for example, the differences in the data sets, the differences in the algorithms that Ankit briefly touched upon. So these are some things that you can start thinking about, start investigating with a test data input set, and start putting this in your report as placeholders or certain language that you want to use ahead of time from your investigation prior to the competition itself, right? Yes. So again, think about what you're doing and plan for contingencies. Consider the number of runs you might need to do based on the test data input set that we will share. So with that, let me briefly look at the Q&A document. So there's a question about the special journal issue. I do not know when the timeline of people are going to be notified for that. This might be a question for Stephen for the historical issue for that. He had to drop out, but I can point him to this question. Will we have a sequential BLearn, which takes a long time to finish? We have already decided the benchmarks to run in the challenge. We are making sure that we are not expecting you to run anything that is so that will take up more time than the competition allows, especially with the other applications you run. And we'll also make sure that the data sets are within reason for what you will be running. So don't expect to run maybe all of the experiment, but parts of it. So think about what could be there and keep that in mind. So I answered the question about what the advisors are. Yeah, you can answer questions. You can answer questions from the students about what these possible differences could be that could contribute to the differences in the results that they're seeing, or any speed up or lack of that they are encountering that Ankit presents in his paper, for example. What can we do to become acquainted with the running code and getting results before the competition starts? So in his slides and also in the FAQ announcements document, there is a link to the Ramble application, which is the reproducibility application. So you can start taking a look at it now. You can start trying to compile it in his GitHub repository, and Ankit provides a lot of instructions for how to do that, and instructions as well for how to run some of these experiments. So you can go ahead and take a look at that now and work on it. What are the typical acceptance rates of the reports? I am not familiar with this. I do not have any much history with this, but I can again point this in Stephen's direction or other committee members. So for access to the Google Docs, if you don't have access there, please, your teams should have access. So ask a team member if they do, and if not, I will post a solution. Yes, thank you, Stephen, for that question. But yes, we can address that as well. But you should have access, and please try to get that. Again, this will be recorded, and we will try to fill in the Q&A, as Steve's mentioned in the chat. We'll try to fill those in later and then put them in the announcements document. I think I covered all the questions though, unless.
That looks like all of the questions. Thanks, Limay.
Yes, and thank you, Steve. Sorry, everyone, that we went a little bit over time, but good luck to you all, and I hope that we will see you in St. Louis or virtually.
Bye, everybody. Bye-bye.
Bye, everyone. Thank you.
Thank you.